All right, so this unit is on atomic structure and periodicity. Like I said before, this is going to be, we're going to get into electron configurations and periodic trends, but we're first going to talk about what light is, electromagnetic radiation. Before we jump into the practice problems, I know you haven't had a chance to read any of this because you just got this stuff today, but so we're going to be talking about light waves, okay, for today. So let me draw a wave. I will say I think mine yesterday was a little bit better. All right, so you may or may not remember this stuff. Like, I think you learned about this back in like physical science, 8th grade science, and if you've taken physics, you may or may not have talked about this already. But some things we're going to be looking at in terms of waves and light are going to be things like wavelength, frequency, stuff like that. What is wavelength? And if you don't know, look on the first page of your guided notes because it's defined there. It is the distance between two successive crests. Which one's a crest in my wave? The top. And what's this called? The trough. Like what a pig feeds out of? Trough. It's not pronounced trow. I always thought it was pronounced trow for like years, and then people were like, no, it's trough. And I'm like, oh. I thought it was trow. Anyway, so this point to this point is the wavelength. Wavelength has an abbreviation, like a variable unit type thing. And it's not W. It is lambda. It's a Greek letter. You know, we use Greek letters a lot in math and science. I think we ran out of the regular alphabet. What's that? The what's the alphabet called? Is it just the alphabet? The Latin alphabet? I don't know. Yeah, I mean it's not the. I don't think it's the Arabic alphabet, but. Oh, okay. Anyway, I think they ran out of like regular like A, B, C, D, whatever to Z, and so then they started using Greek letters. All right, so that is wavelength. Another piece that we're going to be talking about, now just an FYI, we're not going to really deal with this, but what is this called? Amplitude. We don't really deal with that with the stuff this unit. I know that when you're talking about sound waves, the amplitude refers to the loudness of the sound. So the bigger the wave, the louder the sound. But we're not going to deal with the amplitude, but that's just a little aside. Another piece that we're going to talk about is frequency. You've probably heard of frequency like when you listen to the radio. You're tuning to the different frequencies for those radio waves. Radio waves are a type of electromagnetic radiation. What is the definition of frequency? How many waves pass a point in a given, we typically measure in a given second. That's exactly right. So the number of waves that pass a given point in 1 second. Okay? Now, the symbol for frequency is also a Greek letter. Anyone know what it is? It's nu, which is a weird V-U thingy. Nu. Not to be confused with mu, which is the symbol we use for micro, which is a U with a weird tail. All right, so wavelength Wavelength is a measurement of distance. It is a measurement of distance. For all of our calculations we're going to do, we're going to need wavelength in meters. Okay? But sometimes, oftentimes, it'll be given in things like nanometers. So you're going to have to convert. Frequency, the unit is seconds to the -1 or hertz. They're the same thing. Okay. So it's per second. It's really like waves per second, but we just get rid of the waves, so it's per second. Okay. And then the third big thing we're going to talk about is energy, which we kind of already talked about energy before, but this would be like the energy of that light, that piece of light. You know, energy is going to be E. Nothing new there. What unit do you think we're going to measure energy in? What? Volts, that's cell potential. Think back to like thermo. Joules. We're going to do joules. Again, sometimes it might be in kilojoules. You have to convert, but for all of our calculations, we're going to want energy in joules. Okay? All right. So, in terms of the electromagnetic spectrum, the entire electromagnetic spectrum, of what we can see with our eyes of the electromagnetic spectrum, it's a teeny, teeny, tiny portion. We can only see visible light, like Roy G. Biv, and that's going to be in the range from 400 to 700 nanometers. Beyond that, either higher or lower, we don't see that, okay? But it's still there. All right, so let's just jump into some calculations with this, okay? So, number one, we're going to calculate the frequency of light that has a wavelength of that, 6.7 times 10 to the -5th centimeters. So the first formula we're going to use is this. C equals lambda nu. It sounds like I'm stating a sorority or fraternity, like I'm saying it, but again, Greek letters, yay. C equals lambda nu. What is C? It is not a coulomb. C stands for something. Speed of light. C is the speed of light. You know the formula E equals mc squared? That's energy equals the mass of the substance times the speed of light squared. All right, now, is the speed of light constant? Can the speed of light change? The speed of light does change depending upon the medium, the material, that the light is traveling through. In a vacuum, aka space, what is the speed of light? .998 times 10 to the 8th meters per second. That is the speed of light in a vacuum. When you have light traveling through air, you know, that actually has molecules, it slows it down ever so slightly. Water, other things. That's why you get refraction and stuff like that. You know, like when you have like a straw sitting in like liquid and stuff, it like looks like it's bent when it's really not. That's having to do with the fact that the speed of light is changing ever so slightly. We're not going to get into that. That's physics, optics, stuff like that. For our purposes, for everything we're going to do in chemistry, the speed of light we are going to consider it to be constant. Okay? And this is the number that's on your formula sheet, the 2.998 times 10 to the 8th. I will oftentimes just round it to 3 times 10 to the 8th meters per second. If you use 3.00 instead of 2.998 on the AP exam, you'll be fine. Like, it's not going to change your answer enough to make a difference, okay? But if you forget, it is on your formula sheet, so you don't need to memorize it. All right, so we are finding the frequency. Which variable are we solving for? Nu. We're solving for nu. We know C, and we know lambda. Lambda is our wavelength. But notice that our units for C, our speed of light, is meters per second, and our wavelength was in centimeters. And remember before I said we need wavelength in meters. The reason why is because the speed of light is meters per second. So we're going to have to convert that 6.7 times 10 to the negative 5th centimeters to meters. Okay? And what's the conversion there? Divide by 100, because there are 100 centimeters in 1 meter. And what is that? (6.7 times 10 to the negative 7 meters). All right, so now we can plug that into the formula. So speed of light equals 6.7 10 to the negative 7 meters times frequency. And notice our units, we have meters per second, and then we're dividing that by meters. The meters are going to cancel, and we're going to be left with 1 over seconds, which is a hertz, which is the unit for frequency. What'd you get? (4.5 times 10 to the 14th seconds to the negative 1), or hertz. You can write hertz. Either one is fine. Okay? Like I said, everything we're going to be doing today is just going to be manipulation of formulas. Okay? So it's just plug and chug, solve for your unknown. Should be pretty straightforward. You just have never done these calculations. Most of you have never done these calculations before. Okay? Are we ready to move on to the next one? All right. The next one is we are calculating the energy of a photon of orange light with a frequency of that. Now, a photon. A photon is a particle of light. You're going to read about this in your reading tonight. Hey, that rhymed. And so we're going to talk about this more next class, and I know some of you won't be here because of the SOL, but I'll record it, don't worry. We're going to talk more about this more next class, but essentially when you have an element or an atom and it absorbs energy, the electrons will jump up energy levels. They'll absorb energy, they'll jump up energy levels, but then they'll fall back down and they'll emit light. And some of it will be visible light, some of it will be light we cannot see because it's beyond our scope of what we can see with our naked eye. Okay? And so that's the light we're calculating. That's where this is going. Okay? And that's why it's related to atomic structure and energy levels and all that stuff. So the next formula we're going to learn is this. E equals h nu. Again, this is on your formula sheet, as is the constant, which is h. So both of our formulas have constants. We have c, which is the speed of light, and h, which is called Planck's constant. And it looks like Planck with an extra c, but I've always heard it pronounced Planck. Until I was like an adult and already teaching, and then other people called it Planck, so I don't know, but I always called it Planck. And it is 6.626 times 10 to the negative 34 joules times seconds. It's on the formula sheet. Yep. Nothing that I've shown you so far is not on the formula sheet. That's coming next. All right. So, we're calculating energy. We know Planck's constant because it's on the formula sheet. No need to memorize. And frequency, nu, is given right here. We don't need to convert it. It's already in the appropriate unit. And this just happens to be orange light, FYI. Orange light has that frequency. So you're just going to multiply. Notice that seconds and seconds to the -1, they're going to cancel. And we're going to be left with joules, which is why energy is in joules. All right, what do we get? 3.3 times 10 to the what? -19 joules. Okay? Cool? So this one, number 2 and number 3 are related. Okay, if you've looked at number 3 already, you're going to see it's the same frequency. There's just one slight change. Number 2 is asking us about a single photon. This is the energy of a single photon with that frequency. Number 3 is asking us for a mole of photons with that same frequency. What would the energy be? Okay? So for a mole of photons. So we just calculated the energy of a single photon was 3.3 times 10 to the -19 joules, right? So in order to find it for a mole of photons, what are we going to do? Use Avogadro's number, which you should already have that memorized, but in case you forget it, it is on your formula sheet. Okay? So, if we, technically, let's write this like this. 3.3 times 10 to the -19 joules per photon. Because that is the energy for one photon, per photon. Okay? So we're going to convert photons to moles. So, mole over nope, I'm doing that wrong. Photons over 1 mole. How many photons are in a mole? 6.02 times 10 to the 23rd. Because you can think of a photon as a particle, which is why you can use Avogadro's number. So you're just going to multiply the energy for a single photon by Avogadro's number to get the energy for a mole of photons. It should be significantly more because you have a whole bunch of them. Your exponent's wrong because it should be significantly more. Yeah, I got 5. So 2.0 times 10 to the 5th joules per mole. I don't think the calculator gives it to you in scientific notation. I think it's like 196 something, something, something. But 2.0 times 10 to the 5th joules per mole. Cool? We good there? Okay. So, number 4 is we want to know the energy of a photon of light. So a single photon, again, we're not going to do the mole thing, that has a wavelength of 425 nanometers. So wavelength, what symbol does wavelength get? Lambda. And energy is E. Have we used a formula that has energy and lambda in it? together? No. We have E equals H nu, which is what we just used the last couple problems. And then we have C equals lambda nu. We don't have anything with E and lambda. Okay. So, you could, and now both of these formulas are on your formula sheet, okay? So you could solve for frequency in the C equals lambda nu formula and then plug that into the E equals H nu formula, which is perfectly fine. Or you can combine the two formulas, okay? And when you combine them, you get E equals HC over lambda. That formula is not on your formula sheet. I haven't asked you to memorize many formulas. Like the KP to KC formula is good. The Nernst equation is good. This is like one of the few that I say this is a beneficial one to memorize. This is a beneficial one to memorize. Okay. But again, if you forget it, you have the two formulas that you can use to get to that. Okay? So, what do we need to do with lambda? We need to convert it to meters. So go ahead and convert that to meters. There's 10 to the 9th nanometers in 1 meter. Or you can divide this by 1,000 3 times to get to meters. Either one. So you should get 4.25 times 10 to the negative 7 meters. Bless you. Okay, you should get 4.25 times 10 to the negative 7 meters. So then we plug that in 6.626 times 10 to the negative 34 joules times seconds. Speed of light, 3.00 times 10 to the 8th meters per second. That's all over 4.25 times 10 to the negative 7 meters. A lot of numbers with exponents. And what do you get? Four point what? I got 4.68. What was your exponent, Emily? Well, what was your exponent? Oh. Ah, yes, that will make a big difference. And 6.626. I think that might be why you got 4.2 instead of 6.8. All right, what's the unit? Joules. Honestly, depending upon like how you calculate it, you might get like if you had gotten like 4.42 times 10 to the negative 19, I probably would have still accepted it because you had the right exponent and you were probably just a little bit off. Like maybe you typed in 6.26 instead of 6.626. But if your exponent isn't right either, then I know that that was multiple calculation errors. Okay? All right. One more problem that we're going to do today, and then I'm going to talk a little bit more about energy and frequency and wavelength and stuff, and then we'll be done. Okay? All right, the last problem for today, number 5. We're going to be looking at the energy required. We're told that the energy required to break the oxygen-oxygen bond in O2 is 496 kilojoules per mole. And we want to calculate the minimum wavelength of light that can break that bond in one molecule. So O2 looks like this. I'm not going to worry about the lone pairs. So basically, we have light. I'll even use yellow. We have light. We want to know what frequency, or sorry, what wavelength of light is needed to break that bond. Okay? The energy of that bond is 496 kilojoules per mole. And that is for a mole of those molecules. So what do you think we should calculate first? Yeah, let's figure out the energy for a single molecule, because the energy of that molecule will be the energy of the photon that needs to come in to break that bond. Okay? So we're kind of working backwards. So we have 496 kilojoules per mole. We're going to have to convert moles to molecules, and we're going to have to convert kilojoules to joules. Let's handle the kilojoules to joules first. Or I don't care how you do it, but I'm going to handle the kilojoules to joules first. And then I'm going to deal with the mole to molecule. How many molecules are in a mole? 6.02 times 10 to the 23rd. So we're going to multiply by 1,000 and divide by Avogadro's number, and that will tell us the energy for a single molecule. And what do you get? 8.24 times 10 to the negative 19 joules, and that's per molecule, right? So that is the minimum energy for the photon that needs to come in, like needs to at least meet it, and ideally it'll exceed that to actually break the bond. Now let's figure out what the wavelength of that energy is. Which formula are we going to use? E equals hc over lambda, that combined formula. Or you could have done E equals h nu and then plug frequency into C equals lambda nu to find lambda. It's really the same thing you're doing. We're just doing it all in one step as opposed to two steps. Okay. So E is 8.24 times 10 to the negative 19 joules. We can drop off the per molecule or per photon. H is 6.626 times 10 to the negative 34 joules times seconds. C is 3.00 times 10 to the 8 meters per second. And we're solving for lambda. And what do you get as your, have you gotten your lambda yet? Times 10 to the negative 7. What's your unit? Meters. Okay? And there is a certain color of light associated with that. Okay? I just drew it as yellow. It's not necessarily yellow. All right, so here is the electromagnetic spectrum. I pulled this from your guided notes. So, across the top has wavelength in meters. Our farthest to the right are things like radio waves and stuff like that. Those are going to be our longest wavelengths. That's like 10 to the 4th meters. Huge! Huge. okay? And then our farthest to the left, where like gamma rays are and stuff like that, it's like 10 to the negative 12 meters. Really, 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 really tiny, okay? And then all the way in between. You don't need to memorize the order of them necessarily. It's going to be more like you need to understand the relationship between wavelength and frequency, and wavelength and energy. And that's what I'm going to be talking about now. This middle section here, we have visible light. All right, it's Roy G. Biv. Actually, this is backwards because we're going from shortest wavelength to longest wavelength. But think Roy G. Biv, right? I'll write it backwards. You should know the order of the visible light colors. Feel like, yeah, Vibjorn. Sounds like someone's name. Yeah. So, but it normally we think of it as flip, but my picture has it this way. Okay. So, down near the red end of the spectrum, what do you notice about their wavelengths? Longer than the violet end of the spectrum, okay? So in this chart alone, we have long wavelengths over here and short wavelengths over here. The relationship of wavelength to frequency is indirect, all right? There's an indirect relationship between wavelength and frequency. A long wavelength means a low frequency, all right? Because if the longer it is, the less, remember, all of this light is traveling at what speed? The speed of light, 3.00 times 10 to the 8th meters per second. It's all traveling at the same speed, so the longer it is, the less waves will pass per second. The shorter it is, the more waves will pass per second. So that's why a long wavelength is a low frequency and a short wavelength is a high frequency. Okay? Now, frequency and energy are directly related. Okay? The higher the frequency, the higher the energy. And the lower the frequency, the lower the energy. Okay? So, and if you're looking on this chart, visible light is typically going to be times 10 to the negative 7 meters. If you notice, it's 4 times 10 to the negative 7 meters to 7 times 10 to the negative 7 meters. That's 400 to 700 nanometers. So for visible light, when you're converting from nanometers to meters, you're pretty much always going to have times 10 to the negative 7, which is going to make the frequency times 10 to the 14th and make energy times 10 to the negative 19. So just some things to, consistency and things to keep in mind as you're going through this, okay? So, and like I said, you don't necessarily need to know that red is 700 nanometers and violet is 400 nanometers, but you should know that orange light has less energy than blue light, and green light has a shorter wavelength than yellow light. Things like that. You should be able to compare them. Okay? Questions on that? All right. So that's it for today.